Hello friends, in the previous lecture we defined the entropy of a random variable x to be equal to the negative of p of x log p of x when x takes value from an alphabet cursive x. So now here x is a random variable. So it might so happen that there might be two or more random variables as well. For example, if we have two random variables h of x, x comma y, then we can similarly have a joint distribution px comma y for the pair of random variables. So now when there is a joint distribution, we also have a term called joint entropy, which is given by h of x comma y. And h of x comma y is given by, it is defined as x belongs to cursive x, y belongs to cursive y, and these are the alphabets where you can from which x takes values, and this is the alphabet from which y takes values, and this is the negative of p of x comma y log of p of x comma y. So it is a similar definition as compared to entropy. We just have two variables, and it's also the negative of the expectation of the random variable log p x comma y. So once we have this joint entropy, we can also define something called a conditional entropy. For example, if we have two random variables x comma y, and they also come from some probability distribution p x comma y, then we define the conditional entropy. So by definition, this is equal to p of x times h of y given x is equal to x. Now this is like so this is conditional entropy when x takes particular value x, and this is the probability value. So we just have a weighted sum of the entropies, defined by this term, where there is the entropy of y when x takes the value small x, and it is weighted by this probability. So now what is this term? We can further expand this term as, for example, if we have x belongs to p of x times when y takes values from some alphabet y, this will be equal to p of y given x times log p of y given x. But because of the definition of entropy, we will also get a negative term here. So now this is h of y given x. Now what we can do is we can bring this sum over here, and we can further define this to be p of x times p of y given x times log of p of y given x. So now this is equal to p of x comma y log of p of y given x, and this is like negative x belongs to x, y belongs to y, and this is from base rule. So after further applying base rule, what we get is this is equal to negative of the expectation of log of p of y given x. So this is h of y given x. So we have a chain rule now. It's a very important theorem, and this is probably one of the most important simple theorems that we need to know in information theory. And there are other theorems as well, but this is just like one of the most basic theorems, and it's called a chain rule. Now why is it called a chain rule? It is because it gives an alternate definition of the joint entropy in terms of the entropy of a variable and the conditional entropy of the other variable. So this is like the equivalent of Bayes rule in probability, but here instead of a product you'll have a sum. Now it's probably very kind of intuitive as to why this happens, right? Because the joint entropy is now the sum of the entropy of the first random variable added with the entropy of the second random variable given the first random variable. And this is also equivalently, this is also equal to h of y plus h of x given y, and this is because of conditions of symmetry. But let's prove this theorem, right? So now h of x given comma y is given by minus of x belongs to x, y belongs to cursive y, p of x comma y log p of x. Now this is by definition of joint entropy. Now what we can do is we can further expand this log p x comma y using Bayes rule. If we use Bayes rule on this part, then we get, I'll avoid writing the subscripts here. This x belongs to y belongs to y. Px comma y log of p of x times p of y given x. Now, because of this log rule, and you have a negative sign here, this log becomes a sum. So we have, I'm avoiding the subscripts now, p of x comma y log p of x minus p of x comma y log p of y given x. This is the logarithm rule, right? Now, what this will be equal to is, so for example, if you look at this part, this will actually be equal to minus x belongs to x, p of x log p of x minus double sum p of x comma y log p of y given x. Now how do we get this from here? This is because this is, if you look at the subscripts, this is the sum of all probabilities over all y belongs to y. So if we sum this, and this log px does not depend on y. So if we take all values of y, then sum it up, then we actually get px. So this is easily verifiable. This is just like basic probability because y takes all values. Or in other words, what we can do is we can say that this is p of x, and if we take this sum, then we get p of x because this log p of x is independent of y. So this one is obviously h of x, positive of the entropy, and this gives, this part is h of y given x by definition of conditional entropy. So that is how we get h of x comma y is equal to h of x plus h of y given x. So this is a basic chain rule that we have in information theory. We can also write something like log p of x comma y is equal to log p of x plus log p of y given x. And this is always true because we know that base rule is p of x comma y is equal to p of x times p of y given x. And what else can we do? We can take a log, and then this will just become log plus log instead of multipliers.